In real life, when you measure, there are also some measurement uncertainty or measurement errors, because you can't measure things perfectly. It has to do with you read off wrong, or the measuring equipment is wrong, or you have disturbances from the environment and so on. So let's assume that you measure something. Let's say that you measure the width of an object to 50 micrometers. A micro is just a prefix here, meaning 10 to the minus 6, so 1 millionth. This micro is a tenth, is 1,000 of a milli. So let's say that you measure the width or the length of an object to 50 micrometers. And let's say you're uncertain of what the real value is. You make some errors that you estimate to plus minus 1 micrometer. So it means that the true value you estimate to be between 49 and 51 micrometers. So this doesn't mean that you measure exactly 49 or 51, but some value in between 49 and 51. So this is just a shorthand for an interval. So this is what the real length of the object is. And this is what you measure. And this is an absolute measurement uncertainty. Okay, so this is absolute measurement uncertainty. What is the relative measurement uncertainty or error? That is, if you take the absolute measurement uncertainty and divide it by the measurement value or measured value. So the relative measurement uncertainty in our case here would be 1 micrometers, because that's the error we estimate, and the measured value was 50 micrometers. So this is 150, we can cancel the units. So this is 0.02 or 2%. So that's, if you compare the error to what you measure, then you say that the relative measurement error is 2%. And often this can be more giving than more interesting to know than just to know the absolute error. For example, let's say that instead that you measure the distance between Earth and the Moon to be 380,000 kilometers. And let's say that you have a measurement error uncertainty of 100 kilometers. So you're only certain about this to plus minus, up to plus minus 100 kilometers or 10 mil. And then the relative measurement uncertainty here is 100 kilometers divided by 380,000 kilometers. So the absolute measurement error divided by the measurement value. And how much is this? Yeah, it's roughly this, or 0.03%. We had the other measurement where we calculated the measurement. We had a measurement error of 1 micrometer, and we measured it to be 50 micrometers. This could, for example, be if we measure the width of a hair. So the width of the hair, then we say that we have a measurement error of 1 micrometer, and the measurement value is 50. This we saw that it was 2%. So we see that the relative error when measuring the width of the hair is much larger than the relative error when measurement uncertainty when measuring the distance to the Moon from the Earth. So although this is much larger, the error is much larger than the error or uncertainty when we measure the width of the hair, the relative measurement uncertainty is much smaller for the distance to the moon. So in some sense, this measurement of the distance to the moon is better, more accurate than the measurement of the width of a hair. So you can't just compare the absolute measurement errors and say something about how good the measurements are. You have to compare with what you are measuring. Then you talk about relative measurement error. Let's now talk more about how many digits you should have in your answer when you measure something. Then you can talk about secure or safe digits or non-safe. These are not always established concepts which this talk about secure digits and unsafe digits, but the point here is to understand what it means instead. For example, if you have measured the length of an eraser, so let's say we have measured the length of an eraser to 35 millimeters. And we have measured it with a millimeter graded ruler. Then we can estimate the error, the absolute error, to, let's say, 0.5 millimeter. It's hard to read off better than that, or maybe the ruler itself is not perfect. That means that the true length of the eraser, it is in the interval between 34.5 millimeters to 35.5 millimeters. So somewhere in this length, in this interval, we have the true length. We can also write this as this. So this is just another way of writing this interval here. It doesn't mean two different numbers, but it means, in this case, this means an interval. Okay, so we can know that the true length is in this interval. So we noticed that which of these digits are we sure of and which ones are we not so sure of. For example, that the first digit is a 3. That we are completely sure of, because you see, no matter what it is in this interval, it's a 3. And the second digit, we know that it's 4 or 5. So we're semi-sure of what it is. So we know it's either 4 or 5. However, the first decimal, we are completely unsure of, because it could be 0.5, 0.6, up to 0.9 and 0.0. It could be anything. So the first decimal could be anything. So we are only sure of that it is 34.5 something up to 35.5 something. So only these, the first we are completely sure of, and this we are semi-sure of, because we know it's 4 or 5. But again, talking about semi-sure and so on is not always established concepts. But you understand the idea that some digits we are more sure of than others. One practice you can come across is that in an answer, or if you give a length for something, you should only keep digits that you are completely sure of or semi-sure of. In this case, you should answer like 34 or 45. You shouldn't keep the decimal, because it's completely unsure anyway. And of course, if the first decimal is completely unsure, and the rest of the decimals are also completely unsure. But this practice is not used by everyone, so you should be careful not to assume that everyone uses this practice. Often you want to round off a measurement value to some other value. For example, you measure the distance between Gothenburg, or written in Swedish, Göteborg, and Stockholm. So let's say that you have measured the distance between these as 39.7 mil, and mil, that's 10 kilometers. It's not miles, not English or American miles. So if you have 39.7 mil, okay, let's say you want to round it off to whole mil, then 39.7 is closer to 40, so you should round it off to 40 if you want to have an integer answer. And as another example, let's say you want to round off 1.46 to 1 decimal, then you should round it off to up to 1.5, because 1.46 is closer to 1.5 than 1.4. So if you put it on the number line, so if I have 1.4 here, 1.5, then I have 1.45 here, 1.46 here. So you see that 1.46 is close to 1.5 and 1.4. However, if you have 1.45, it's just as close to 1.4 as 1.5, so you could round it off to any of these two. However, sometimes in these cultural conventions that you should always round up. If you have 1.5, you should always round up to 1.5. But that's not the logical rounding off. You could just as well logically round it down. So you have to keep in mind that that's a cultural convention. A digit that is in some sense you're more sure of than others, then you talk about significance figures or significant digits. And then you say that every digit in a number is significant, apart from if you have zeros starting the number, or if you have zeros ending number that does not contain a decimal number. So let's take some examples. For example, the number 2 has one significant figure. Let's write SF. It has has one significant figure. And 225, it has two significant figures. 205 has three significant figures, because here I have 0, but it's not in the start and not in the end. 34.5 has also three significant figures, so it doesn't matter here if it's decimals or not. 40, that has only one significant figure, because it ends with a 0 and is not in a decimal number. If we have 4.0, then it has two significant figures. Then you should really count this in, because it says something about accuracy. This does not. It's also saying of the magnitude of it. 40.0, it has three significant figures. Again, it ends with zeros, but it contains a decimal number. So it tells you a little bit about the certainty of the digits. Here we have three significant figures. However, this one, for example, it only has two significant figures because it starts with a 0. Or this one, it only has one significant figure because it starts with zeros. And finally, the final example, this one has two significant figures. It has these do not count, but this count since it ends the number, but it contains a decimal, so it counts. So these two are significant. However, sometimes you should be a little bit careful about saying that how many significant figures, for example, numbers like this have, because it's hard to say if the person that has written 40, for example, does he really mean exactly 40? Has he just rounded off to the closest 10? Or is he unsure if it's 39, 40, or 41? So if these zeros tell you about something about accuracy or not, it depends really on the situation, which conventions they use, so one should be a little bit careful. However, you can give the answer in normalized notation if you are unsure. For example, if you give in normalized notation, that means that you give a number here, x, could be plus or minus, and this number should be between 1 and 10, and then you give a power of a magnitude 10. So if you give the number in this way, well, x is here a number between 1 and 10, and k is an integer, then you write in the normalized notation. So for example, if you want to write this in normalized notation, you can write it as 4.5 times 10 to the 3. And then here now you can give as many zeros here depending on how significant, how sure you are about this number. So if you really meant that these 2 zeros doesn't really count, then you should answer like that. But if you really are sure of that these zeros should give some information about how accurate your number are, you could write it like this. So writing in normalized notation, this number here, the significant figures of this, tells you some information about how accurate your number are, how sure you are of your digits. Because now you have put the magnitudes separately. Here is like a mix of the magnitude and how many digits you are sure of. So it's better to write in this way if you want to signalize or give information on how sure you are of the digits. Let's take an example. Let's say that you have a measured length to 1500 meters, and you have an absolute measurement uncertainty of 0.5 meters of measurement error. That means that the true length, so the true length, let's call it L, is 1500 meters plus minus 0.5 meters. So it's in this interval. Remember now, this is a symbol for interval. So it means that the true length is in this interval between 1500.5 to 1499.5 in this interval. So the true length is in this interval. Okay, we see here that the first digit we are completely sure of that one. The second digit we are almost sure of. We know it is 4 or 5. The third digit we are also semi-sure of, is 9 or 0. And also for the fourth digit is 9 or 0. However, the decimal we are completely unsure of. It could be anything. So we are sure or semi-sure of the first 4 digits. So here it seems reasonable to give the answer as this. Because we are sure now, so we should have 4 significant figures. So now it seems reasonable to answer like this. So how many you should keep among significant figures depends on your absolute measurement error here. So if you write it like this and can figure out which digits are sure or not, or semi-sure, then you only keep those digits are sure or semi-sure. Then that gives you a number of significant figures you should keep. But remember that not all people follow these conventions, so you always have to look at the context, what you should do. Let's say you have a mountain and you have several people have climbed the mountain. And let's say that several thousand people have climbed the mountain. And let's say that the height of the mountain is 5,234 meters. And after several thousand people has climbed the mountain, they have wore down the peak with 1 millimeter. Because a lot of people step there. Should you now update your height, should now it's update to 5,233.999 meters. Should we write a new length as this? No, that doesn't really seems reasonable, because the measurement uncertainty in this is probably much larger than the millimeter anyway. So you should stick to the old one. But of course, if this would be exact true length, then you could of course start to think about this, but it doesn't seem reasonable that this is the case. The uncertainty in this is much more likely to be larger than 1 millimeter. So you shouldn't update your measurement value. Let me say that let's assume that you add or subtract or multiply or divide measurement values. How many digits should you give in the answer? That's often something you can come across. Then we have some rules of thumb for doing that. But one should remember that rules of thumb, but they are not exact rules, so they can of course give you the wrong answer. If you add measurement values or subtract, then the rule of thumb says that you should have as many decimals in your answer as the term that has the least number of decimals. For example, if you have 12.3 and add to that 4.56, then the answer will be 16.86. This has 1 decimal, this has 2 decimals. Then you should really look at the one who has the fewest, because the uncertainty in this one is probably likely to be larger than this one, since you're only giving 1 decimal and here 2. So the answer you should round off to 1 decimal. So in this case you should answer as 16.9. But again, this is rule of thumb, so it just gives you some direction of what to do. If you instead have a multiplication, okay, or division, what kind of rule of thumb should you have then? Then the rule of thumb says that you should have as many significant figures in your answer as the number that has the least number of significant figures. So let's say that you measure the width of a rectangle. So let's say it has a width of 5.2 centimeters and the height of 1.46 centimeters. What is the area? Yeah, it is of course 5.2 times 1.46 square centimeters. And if you calculate this, it will give you 7.592. How many decimals should you answer here? According to rule of thumb, you should look at the one who has the fewest significant figures. So which one has the fewest significant figures? It's this one. It has 2 and this has 3. So you should answer with 2 significant figures. You should have 7 point and rounding up to 1 decimal here. So that's the rule of thumb for multiplication and division. However, rules of thumb, like it says in the name, they're not completely reliable. So sometimes you want to be more careful than just using rule of thumb. So let us just finish off by looking at what can you do if you want to be more careful than just use this rule of thumb. So let us take this example with the rectangle again. So let's say we have the width of 5.2 centimeters, or the width, the length, or the width of 1.46 centimeters. Now we want to calculate the area, and we want to answer more carefully than just giving rules of thumb. Let's assume that the measurement error, absolute measurement error in 5.2 is 0.05 centimeters. And let's assume that the absolute measurement error in this is 0.005. Why have we chosen this one? Because we have thought that this value, we think that this has been rounded off. And if it has been rounded off to one decimal, the true value must be between 5.15 and 5.25. So the error here should be plus minus 0.05. Same here, if we think that this has been rounded off to 1.46, we think that it has been rounded off of 1.455 and 1.465. So it has been rounded off, so it's plus minus this number here, the uncertainty. That's how we've been thinking here. Of course, we don't know if it's been like that, but let's assume that the absolute measurement errors are like this. Okay, then we know that the true lengths of the sides, for example, the larger of the two, the true length of that one is this. And the true length of the other one is this. Now we want to estimate the area. So let us first see what could be the smallest possible value we could have of the area. Yeah, then we take 5.2 and then we take minus this one. So then we have this. And the smallest of this one is 1.455 centimeters. And how much is that if you do it on the calculator? This much. And largest area we could have, what is that? And if we take the other extreme, this is 5.25. And this is as biggest is 4.65 centimeters. And if you use calculator here also, we get 7.61 9125. Okay. So this is the smallest one it could be. This is the largest one it could be, taking into consideration the errors. So let us give the answer as the average between these two. So what is the average? Okay, so we add these two. And that will give us okay, so now we want to give the answer like this. But how many digits should we keep? Okay, so we see here now that what is the uncertainty? What is the uncertainty of this? This is the average. So let's say that this represents our measurement. But what is the measurement error then? If we take the largest minus the smallest, so measurement error here, the absolute one. So if you take 69125 minus the smallest one, what do we get then? we will get like this. Okay, so now we want to give the answer then in. So this here is our average estimation of the area. And then we have plus minus, but not plus minus half of this. So we take half of this, then we have 0.99. Okay, but it's not reasonable to answer these many decimals. We are not that sure of our answer. If we just look at what we started with, just having 1 decimal, 2 decimals. So how many decimals should we have? If you look at this now and compare it to what its minimum and maximum could be, we'll see that we are completely sure of the first digit. The second digit we are sure that is 4, 5 or 6. Then the third digit we are completely unsure of. So we don't know anything about it because it could be 9, 0, 1. It could be anything. So we should only stick to 2 digits here. And rounding off to 2 digits, you should get 7.6. And of course, if this digit is completely unsure, and the rest are also completely unsure. So we round off to 1 digit decimal here. And rounding off this to 1 decimal is like this. So the best we can do is to give the answer like this. So this is our best answer. And here we have, if we give it more carefully than just using rules of thumb. So this is then we have come up with them. But we could of course compare what did we get if we use the rule of thumb. Yeah, if we go back now to the rule of thumb, what did we answer then? Yeah, we answered 7.6 with the rules of thumb. If we remember what we did there. So the rules of thumb in this case gave us actually the correct answer. But now we have also a little bit more sure about exactly on the error here, the absolute error. So for all this measurement analysis, one can do it even more carefully. You can use differentials and so on, but the point here is just to show some aspects of it. It feels a little bit more on shaky grounds than other chapters on this mathematics, because you're using rules of thumb, and it's not always sure that people use conventions and follow the same standards and definitions. So you have to keep that in mind. So this at least you give you some sense of how to estimate measurement errors.